let's dive into one of the most famous and most misunderstood molecules in your brain, serotonin. Yeah, the happy chemical. We've all heard that, right? It's simple, it's catchy, and well, it's a massive oversimplification. Today, we're going to see just how massive. Because the real story of serotonin isn't just about feeling good. We're talking about a fundamental chemical code that regulates, well, pretty much everything your brain does. So scientifically, it's known as 5-HT, and its real job is to be a master modulator. Think of it less like a simple messenger and more like the conductor of an orchestra. It's not just playing one note, it's fine-tuning the entire symphony of brain activity. And the scope of its influence, it's absolutely staggering. I mean, we're talking about everything from how you learn and remember things to how you process rewards, even your basic sleep cycles. Yep, serotonin has its hands in all of it. So you're probably wondering, how can one single chemical do so much? And that's a great question. The best way to think about it is with a simple analogy. Imagine serotonin is a key. Now, the brain isn't just one big door. It's filled with tons of different locks. The magic isn't in the key itself. It's all about which specific lock it opens. So just how many types of these locks are we talking about? Well, scientists have found at least 7 major families of them. And in neuroscience, we call these locks receptors. Each one, and this is the important part, kicks off a totally different chain reaction inside a neuron. Okay, so what actually happens when that key turns in the lock? This is where it gets really, really cool. It turns out serotonin can send 3 very different kinds of messages. Let's break them down. All right, message number 1. For some of these locks, like the ones in the 5-HT1 family, serotonin acts like a dimmer switch. It fits in, turns, and tells the neuron, hey, quiet down a bit. It actually inhibits the cell's activity. But then, that exact same key can fit into another type of lock, say a 5-HT4 or a 5-HT7 receptor, and do the complete opposite. Instead of a dimmer switch, it's like a volume knob. It cranks the activity up, exciting the neuron and making it much more likely to fire off a signal. See? Same key, totally different result. And then there's a third type of lock that's in a class of its own, the 5-HT3 receptor. This one isn't a dimmer switch or a volume knob. It's a gate. The moment serotonin binds to it, whoosh, a gate swings open, letting charged particles flood into the cell. It's an immediate, super fast response. So let's just recap, because this is the whole point. You have one single chemical sending 3 completely different messages. It can say slow down, it can say speed up, or it can say open the gates right now. It's this incredible flexibility that makes serotonin so powerful. But whenever you have a system this complex, this intricate, there's a lot that can go wrong. So what happens when the wrong message gets sent? Or maybe a message doesn't get sent at all? Well, this is what happens. When this system goes haywire, it's not a minor glitch. We're talking about a direct link to a huge range of neuropsychiatric disorders. Let's take a closer look at this. So something like depression, you can see that a whole bunch of different receptor types are involved. But for migraines, it's much more specific. It's mainly linked to a few receptors in that 5-HT1 family. You remember those, right? The dimmer switches. This just proves it's not about having too much or too little serotonin. It's about which specific locks are malfunctioning. And this, right here, is one of the biggest challenges in developing treatments. How do you design a drug that fixes just one of those broken locks without messing with all the other ones that are working just fine? It's like trying to fix one switch in a massive interconnected power grid. Because here's the problem, right? As our source material points out, a single type of receptor might be involved in mood in one part of the brain, but it could also be involved in, say, digestion in another part of the body. So if you create a drug that hits that receptor everywhere, well, you've just discovered the root cause of side effects. This really brings the whole story together, doesn't it? On one side, you've got this incredible, intricate signaling machinery inside the cell. And on the other side, you have the huge variety of conditions that can pop up when any single part of that machinery breaks down. They are, quite literally, 2 sides of the same coin. So where do we go from here? Well, the goal isn't to create a master key that just floods the whole system. The future is all about precision. It's about designing smarter keys, brand new drugs that are so precisely engineered they fit only 1 or 2 specific locks, while leaving all the others completely alone. And that leaves us with a pretty incredible thought to end on, doesn't it? As we get better and better at mapping this complex system, and as we learn to design these ultra-specific keys, just imagine
What conditions that seem so impossible to treat today might we finally be able to unlock in the future?